transition graphs. So in fact, we call them domain transition graphs when we generate them in the code. So the idea is that if I have a domain transition graph for a truck, I can have two locations for this truck. In this problem, here's the location 1, here's location 2. The package is at location 1, the truck's at location 2, and I want to basically bring the package over to location 2. So I have a representation of location of each truck. I have a representation of the location of the package, and that includes being inside of the truck and at each location. And I create edges that represent the actions that I could perform over the truck, and edges through the package similarly. And if you remember, the orienteering planner also had some interesting looking graphs that looked very similar to this in terms of where the location of the rover, for instance. So one difference is that we're encoding it as IP, so we can do some fun things like encode the fact that if I'm loading, then I will be still at the same spot. So basically, if I want to load, I need to be at location 1, and so I will I will encode the fact that I have to be at location 1 in order to load at location 1. So all of this is encoded into an IP, and it's very different than the planning graph representation. And the idea is that we're capturing more mutual exclusions, and we can get a better quality heuristic out of this. So this solves the linear program relaxation of the integer program version of this problem. And it turns out to have the heuristic is overall better quality than SPUDS and SAPA PS. But the heuristic is slower than SPUDS because you're actually encoding this relaxed problem as an entire relaxed problem as an IP. And this can affect the scalability of Bebop if there are a lot of interactions between each of these fluents. So if you have a lot of packages and a lot of trucks that interact with one another, the scale up turns out to be very, very poor. But if you have a planning problem where each of these objects will be decoupled, it turns out that the scale up is quite good, and it does better than both of these other approaches. And just the last little trick that's used here is it uses a look-ahead search, and it turns out to be, which means that it extracts a relaxed plan, and it uses that relaxed plan to try to execute actions to get closer to the goal. And this is an anytime optimal approach. Basically, because of this look-ahead, the heuristic is a admissible heuristic, but because we use this look-ahead, we might actually reach a solution sooner than we would reach the optimal solution. So this is an anytime optimal approach. It uses a breadth first branch and bound, which is the name of the planner, branch and bound overscription planning. Okay, so here's the big question. What wins? I already went over this. The scalability tends to be in this way, where MVP is optimal but terrible in terms of scalability, at least using the SPUDS solver. And heuristic search tends to be quite good. These are taken from 2 recent papers. This is Gamer. It turned out to win the planning competition. If you recall, this was the slide that I only had one slide for the planner because it was quite a simple idea where you just take a breadth first search, first going in a regression direction, then going in a progression direction until you meet. And it turned out that this approach did very, very, very well. Much better than the HSP star P, which I also went over in another planner called MIPS XXL, which uses external memory. And here's where the compilation comes in. So the question is, how does compilation do? Here are the net benefit, specialized net benefit planners from the competition on some domains from that competition. And it turned out that the best of those, again, was Gamer. But when you do the compilation, if you use a planner called HSP star 0, which is different than star P, all star 0 is just the regression search part of HSP star P. It turns out to give more solutions. Its coverage is higher. And since these are optimal planners, the quality will be optimal.
Did you try that with some of the newer optimal planners?
I'm sorry?
Did you try the compilation with some of the newer optimal planners?
Oh, this isn't mine. You'll have to ask.
Yeah, well, yeah.
But you're talking about the LM cut heuristic?
Well, maybe not LM cut because it doesn't like action costs, but landmarks, structural patterns.
Yeah, I don't think they have. I don't think.
Okay.
And I guess they were all for additive reward, particularly additive over the goals.
Right.
Yes. So now here's a selection of planners. Yoshi PS was also included in this, although it was not in the last planning competition. MIPS XXL and SG Plan were. SG Plan was the only planner that entered into the satisficing track of the planning competition in 2008. So it turned out that there was no planning competition for the satisficing track of net benefit in 2008 because there was only one competitor. And then MIPS XXL, this is a version, this is the optimal version of MIPS XXL, so this is actually comparing this optimal version. So it's kind of depressing that this optimal planner looks like it's doing better. But so this is Llama, this is the winner of the cost satisficing planners in the competition, and when you use this compilation, it actually does quite well. It gives you 97, which is a big increase. So this is, by the way, just a count of the number of problems solved that in which all of the all of the solutions, all of the planners found a solution. So this is the count of the winning of the winnings, not whether they solved it or not. Okay, so I think we're on time. No, we'll just pass on time. So
4 is when again you get back, right?
4 we get back, yes, 4 o'clock.
But actually,